Hi there. Today we continue talking of string theory, and actually we have a super impressive theme. It's all about units. Cause well, it's really interesting to know what are we really counting in all of this stuff in string theory. What are the ranges? What is it all in centimeters, kilograms, and to which power we should scale it up to have something so small as a string. So, well, we'll explore it today. At the first place, let's discover what variables will we make equal to 1. I.e., look, the speed of light is quite a universal thing. It's a maximum speed of everything. It's from the general relativity we know it all about. So why not to make it 1? So it will be 1 to make everything easier in our countings. Next variable is h bar. It's from the uncertainty principle. And it will be really useful to make it equal to 1 as well. So following, you know that the gravity is uniform, and wherever we go, we'll have to face with gravity. So by Newton, it's as well uniform. So let's make it equal to 1. What for we make it all equal to 1? To actually make our calculations easier. Because wherever we are, wherever we go, whatever we count, we'll have those constants in our solutions, all of those things. So when they are equal to 1, everything becomes really easy to solve. So, just for you to know. Now, to make everything really easy, kind of to know about the lengths and all of this stuff, we need to count from those variables that we made equal to 1, take their real values from the real world, and we'll count the length, the time, and the mass, so that we really know uh, which ranges and which scales we use in string theory. So let's make it. At the first place, let's think what are the units of the speed of light. You know that it is length or distance over, sorry, it's better to say distance, over the time. So it will be length over seconds. So you see, um, it was easy. Uh, well, next, what will be the h bar? H bar is famous from the equation E equals omega times h bar. So we'll derive it from this equation. So don't be afraid of those words. So we basically divide energy over the frequency. What units is the frequency in? Well, the inverse seconds. So and the energy is nothing but the power times the distance. So I believe you know the formula well. A equals F times S. So from it we found this. So it's all about newtons times the distance L. And what are newtons? They are, we are able to um, find them from the formula F equals ma, where a equals m over sorry, I write everything in c, um, are when where the acceleration equals to L over c squared s squared. So that's what I wrote here, m times L over second squared. We multiplied times L, this L, and S. That's from here, because it was negative in the denominator, it becomes positive into the numerator. Now we just cancel everything out. Look, we are able to cancel out the S. It cancels out, kind of S, S squared, we cancel it with S. So, and overall we have mass times L squared, because there is second L, uh, over S seconds. And those are units of the h bar. So now let's work out the units of G, the gravitational variable, constant, sorry, the gravitational constant. Uh, we are able to find it or derive from the equation F equals G times m squared over the length squared, or better to say radius length. So that's what I did here. I found G. I again substitute the force by this thing. We counted it already. It's mass times the length over the second squared. And then I again cancel. The mass cancels out, like in denominator here. This denominator comes from this part. We cancel it, the mass on the top, and overall we have this thing, length to the third degree over second squared, and again over the mass. So now let's actually make the real substitution that we wanted to make. Substitute by these variables of h bar, c, and g, the length, mass, and time. So what we make? We need to guess what the length will be, kind of, in terms of those constants. Yeah, you see. So what I do? Look, we know that G, and H have this part of mass. You see, it's present here and here. G and H. But we do not need any mass for the L. So we need to cancel it out. And you see here in G, the mass is in denominator. And in H, mass is in nominator. So kind of you have 1 over m, and m. What you need to do to cancel mass? Well, you need to multiply them. That's what I do here. So after we did it, after we cancel out the mass, we write the c times to the pth degree. Yeah, to the pth degree, because well, nothing, in case we count, you'll see we won't be able to cancel the seconds and the length without using c. So let's remove this. So now we go on forward. We write everything down, the G, and let me use another color. We write G. After it we write the H. And you see, again, as I told, masses will cancel. And after it we'll have to deal only with length and seconds. Well, in case we sum up the degrees, kind of, look, those. Length to the third, length to the second, seconds to the second, seconds to the first. So we'll have length to the fifth, because 3 plus 2 equals to 5. And seconds will equal to 2 plus 1 to the cube of the seconds. So we'll divide over it because here the seconds are in denominator. And we rewrite the L over S. It's our speed of light. As you remember, it's length over seconds to the pth degree equals to L squared. That's what we set it equal to. What for? To remove the square roots. You'll see. So what we do? We have L to the fifth. This equation, yeah. So now let's multiply this way. So kind of by the rule of proportion. L squared over 1 equals L to the 5, S to the 3, S to the third. So we'll kind of do this. So we'll have this L squared times S to the third over L to the fifth. And in case we can now actually cancel those signs. You see, L squared and L to the fifth partly. We cancel them and have in the end L to the third in denominator. So it's S to the third and L to the third over L to the third. And look, the right part looks the complete opposite. It's S over L and it's L over S. So we'll actually need to turn it around, how would I say? And because of it, we'll have this minus sign. Third because of, well, it's to the third degree. I think you remember the rule of degrees when you have L over S to the minus first. You're able to turn it into S over L. So that's what I did. So we have P equals to minus 3. It's awesome because now we are able to substitute it here. As you remember, it was G times H times C to the pth degree. So now we insert minus 3 instead of the P. So we have G times H times C to the negative degree of 3. So negative degree is becomes a denominator. So that's what happened. So L squared equals to G times H over C to the third degree. Awesome. We found the length. We found the length units. Probably it was a little bit hard or hard. I just want to say you that you did a great job. And those units will be everywhere. So it will be useful to remember that it's G times H over C to the third. That's L squared. So don't forget to take a square root out of it to get the L. So, and what about the T? Will we make the same calculations? No way, actually. No. T here is actually the L that we found over C, because, well, T equals the distance. Oh, again, I'm writing distance over the time, distance over the speed. So over the velocity. So that's what I did here. We take our length over the speed of light. We put it inside, and look, when you have 1 over c, when you insert it under the square root sign, you actually square it, so it becomes 1 over c squared, and 1 over c squared times 1 over c cube. Well, you sum the degrees, and you have 1 over c to the 5th degree. So this is the time. And look, it was much easier. So you did a great job. We found two two, how would I say, two variables of our world into the string theory, and it was great. So what we are left with is the mass. So we'll find it. Um, Mass. What's it? Again, you remember that we have uh, in G we have 1 over m. Yeah? Am I wrong? Let me check. No, 1 over m. M is in denominator. And in H bar, we have m in the nominator. So, to get the mass squared, again, I do this because of those square roots, because I don't want to have those square roots here. So, you see, it's this thing that worries me. So, uh, we'll actually divide them one over the other, and to get this mass squared, we will divide h over g to get the actual mass squared in nominator. We don't need it in denominator. Yeah. So times again c to the some power of p. You will see why, because again, not there. It's not so easy here to just cancel everything out without c. So what we have, we rewrite the h and g. I turned it around, as you see. So the h was, as you remember, m times l squared over s, and g was equal to l to the third over the m s squared. So we turn it around here, and that's what happened. Sorry, may I? Awesome. So I turned it around, and again, look, some terms cancel. Uh, for instance, the L squared with L to the third, there will be only one L down there, and S squared with S, so there will be only one S in the nominator. Plus M squared, definitely, because 1 plus 1 is 2. Don't you mind that 1 plus 1 is 2? So, uh, so, so it was a joke. Following. Uh, in the end, we have m squared equals to m squared times s over l. And look, m squared, we are able to cancel it out. So m squared over m squared equals 1. So kind of we make it so. As you see what I did here. And after it, we have s will we have 1 equals s over l times times l over s to some degree. Well, it will be obviously 1, because we need l and l with s and s to cancel to have 1 in the end. So p will equal to 1, actually. And in case p is 1, well, we insert it in our formula. You remember, m squared was equal to h bar over g times c to the p, where p equals to 1 now. So we have this. So in the end, we have length, we have time, and we have mass. Those all are actually quite real, and they are named Planck, Planck length, Planck time, and Planck's time, Planck's length, and Planck's mass, all in the honor of Mr. Planck, because he was really smart and came up with the H bar, actually. And all of these tiny things. He was the beginner and the starter of the quantum mechanics, one of the starters. So, and in case, don't forget these formulas, they are not so hard. Again, length and time are connected to one another because of this c. They're only different because of third and fifth terms, and mass is this. It's h bar times c over g. So, in the case we count the real numbers, that's the most amazing. The Planck length will be this number. Uh, Time will equal to this, and mass will equal to this. And this is astonishing, because all of those strings vibrate, oscillate with the Planck's time, T Planck, and they all are in the range of uh, Planck length. Isn't it amazing? And the energy we need to excite, for instance, an electron to its excited state is equal to the Planck's mass. It's just fantastic. And by the way, this number is really huge because it results in a huge energy. Yeah, especially for those scales, is just enormous. Almost equal. It's equal to actually the energy you're able to get from burning a whole tank of fuel. Isn't it amazing? Just fascinating. You're able to cross around your country, uh, having only in your engine this mass. Yeah, fantastic and astonishing. So, this was all. Thanks for watching and have a great time. Don't forget to subscribe and like the video. Bye.